All right. Well, good morning, everybody.
Good
So we
morning.
have here the June 22nd meeting of our little group of cosmology discussion group. I've got a presentation today. I'm going to talk about fixing Einstein's mistakes. And basically, dissidents complain a lot about relativity is wrong, but we don't hear anybody really talk about how to fix it. So I'm going to talk about how to fix it. And that's kind of innovation for dissidents because dissidents don't really work on that subject. They want to talk a lot about what's wrong, but don't want to talk much about what's how to fix it. So, all right, fixing Einstein's mistakes. Now, can everybody see this?
Yeah.
I'm thinking about going to the slideshow and seeing what happens if I do a slideshow mode. Okay. Oh, is this better?
Yeah.
All right. Unfortunately, I've got the bar and oh, there it's gone. All right. So fixing Einstein's relativity mistakes. Um, so we got some objectives here. I'm going to formulate a rigorously correct mathematical formalism, replacing the incorrect Minkowski space mathematics. Um, Now, those are a lot of fancy words that mean basically we're not going to be doing the flaky way that physics people do mathematics. We're going to try to use rigorously correct mathematics. Mathematics that you can actually prove is correct rather than you claim it's correct because you did it 1,000 experiments that claim that you proved your theory was correct, even though it's full of math mistakes. Now, we've had lots of presentations over the years in the CNPS Saturday morning discussions where people have shown, well, Einstein screwed this up and he screwed this up, made these mistakes. So we know that the relativity is full of mistakes and errors. Okay, so the next thing we want to do is we want to try to figure out what's wrong with the physical principles, and then we also have a problem with the metaphysical principles. Well, it turns out they're kind of related, the physical principles being wrong and the metaphysical principles being wrong are related. Main one being this idea that Einstein's um, metaphysics, that there's no such thing as absolute time or space, replacing metaphysical ideology of the Newton's physics with a metaphysical reality, metaphysics of Einstein now. I think we've talked about that. Roger talked about that a couple of weeks ago. Okay, so we're going to start off with what are the correct physical principles? Well, the Lorentz theory is the correct theory. And yeah, well, if you want to quibble, you can quibble, but that's the basic underlying assumption I'm going to use here. The Lorentz theory is the correct physical theory. And the reason is because, as it turns out, you cannot construct a rigorously correct mathematical theory using the relativity as your mathematics because it's full of mistakes. All right. Um, there's one and only one locally frame of reference for the application of linear algebra mathematics, only one frame of reference for calculations. So what's that mean? So Einstein's big mistake is he's got this relativity principle. He says, well, I can have multiple rest frames. Well, that doesn't really work except if you stay in the one rest frame. And so what they do is they do experiments in laboratories, and a laboratory is a single rest frame. And they go, oh, Einstein's theory is correct, but that has nothing to do with their metaphysics, that there are multiple inertial frames, The speed of light's the same. They're all equivalent. Now, no, none of their experiments test the postulates. And then the other thing is that a frame of simultaneous time measure is valid. Now we know that that's one of the things that Einstein claims. He claims relativity of simultaneity. That's just a confusion factor. But we know in GPS that we have a simultaneous time in the GPS system. So we know that's possible to construct such a frame of reference. So that basically invalidates Einstein's right there. So now we know that Einstein's theory is wrong. GPS shows that it's wrong in a practical system. How are we going to fix it? Okay, the velocity of light is c only in the absolute rest frame. Now, yeah, that's kind of, I think, the big mistake. Lorentz was on the right track, and then Einstein messed everything up with his multiple. The speed of light is c and multiple inertial frames. That doesn't really make any sense. Okay, the correct physical interpretation involves the theory of what is measured, not time and space changes, i.e., it's a theory of measurement. So what we're talking about is not metaphysics. It's not, speed of light's a constant, metaphysical ideas, physical ideas that can't really be verified by an experiment. It's we're just going to talk about how we do measurements. So what we're talking about here is a theory of measurement, not a metaphysical theory about space and time. All right. Absolute time and space can be established in the measurement rest frame, which is unique locally. Now, people say, well, what about the CMB? That's a rest frame. The Earth is not, we can't, we're just going to talk about measurements that are done, in a frame in which we, understand. And a good example of that is the Earth. So basically, we're going to construct our theory based on the assumption that there is one and only one rest frame. There's a reason for that. There's a mathematical reason for that. If you don't adopt this assumption, you're going to get paradoxes and all kinds of flaky results, which is why relativity doesn't work. It's bad mathematics. You have to assume this one unique rest frame in order to do the calculations and get good mathematics. If you don't do it, you don't get good mathematics. The velocity of light, okay, so we're going to say the velocity of light is not c in an inertial frame in relative motion. Okay, so that's the Lorentz theory, okay? So if I'm moving with respect to the rest frame, the velocity of light that I measure is not going to be c, okay? It's c in the rest frame, but it's not c in my moving frame. So we've basically done away with his two postulates right there. We got rid of both of his postulates. Okay, now we have auxiliary variables for space and time coordinates exist, which transform the measurements to make the velocity c in a moving frame. And that's what the Lorentz transformation does. Now, if Einstein sort of does everything backwards, and that's really an important thing. I mean, it's like his brain works in reverse from a normal brain. He used the Lorentz transform to say that time and space change, okay, because the velocity of light is c, all right, and therefore to explain why the velocity of light is constant, or c, in the moving frame. So we measure it to be c in the rest frame, and we measure it to be c in the moving frame, although it makes no sense that it would be c in the moving frame. So he fixes that problem by say that space and time coordinates change. That's not how we're going to do things here. We're going to do things the correct way and the straightforward way, which is that there's a change of variables, so we can substitute different variables into the equations, and these variables that we're going to substitute are calculated according to the Lorentz transform. And when we get these, and these variables, when substituted into the equations, will give the velocity of light. C is the same in the moving frame, that C, velocity of light is C in the moving frame as it is in the rest frame. But the variables that we use in our transformation calculations are not the same. They're not the same variables. Okay. Now that sounds like it's similar to relativity says time and space changes. All we're saying here is that we change the coordinate variables in the equations. Okay. So I'm going to talk a little bit about coordinate transformation principles. The standard mathematical theory of coordinate transformation found in textbooks can be applied to the Lorentz transformation solution. So what this means is that we're going to take what's already in the textbooks. They already have Lorentz, a standard theory of coordinate transformation in textbooks, in math books. It's been in math books for many years. It's rigorously correct. It's been thoroughly and completely proved and discussed by the mathematicians for many, many years. So all we have to do is go to the textbooks and look at the theory of transformation of coordinates in mathematics textbooks. So we're just going to borrow what they say in those books. Okay. Now, if we do this, if we go and look in the standard in the textbooks, we find out that special relativity doesn't really work according to the mathematics that they use. So special relativity must be wrong since it doesn't agree with the standard mathematics. Okay, now here's the key point I want to make about this. Oh, I forgot to mention about following the standard textbook theory, we must reject the SR solutions because the special relativity solutions violate the unique identity element theorem that forms the basis of linear algebra. Okay, now that's a big mouthful. What is this unique identity element theorems? Well, it's a theorem that says you can only have one frame of reference. If you don't have one, if you have more than one frame of reference, we don't guarantee the solutions will be unique if you use linear algebra. Okay, here's a key point, linear algebra. Okay, and you have to know what linear algebra is. That's beyond the scope of this little talk. But linear algebra basically is a algebraic system that's built up of groups. Okay. You have the additive group, and you have the multiplicative group, and then you have vector space that goes into that. Okay, so special relativity doesn't work in a linear algebra because it violates the unique identity theorem of algebra because it assumes there are two rest frames, and the algebra doesn't work if you assume two rest frames. Okay. And if we look at the algebra books, we'll find out that there are four kinds of transformations. There's the basis change transformation, going from from the rest frame to the moving frame, basis transformation from the moving frame back to the rest frame, and then you have a coordinate transformation that goes from the rest frame to the moving frame, and another coordinate transformation that goes back from the moving frame to the rest frame. Now, that's really a lot of stuff. How do we know about this? Okay, well, a little bit of history here. I didn't know anything about any of this stuff until I knew a little bit about linear algebra. I knew there were problems with special relativity, and I discovered this paper by Hasio by I, who's a Chinese guy, and he has a paper on solving problems of relativistic statics. And it's in physics essays. And he addresses what's known as the Lever paradox. Now, this is a complicated paradox, but it's well known to relativity and relativity books and the relativity literature. It's kind of probably one of the most important paradoxes next to what the more famous twin paradox. What happens is that if you apply the relativity equations, it doesn't work out. And so what they do is they suppose that there's some additional energy in the moving frame that keeps the lever from twisting, because the lever is supposed to be turning when it doesn't turn, and they can't explain why. And so anyway, I don't want to go into the whole detail of lever paradox. That'd be a whole nother lecture right there. Okay, so what he did was he solved this problem, and he solved it using 4 different ways of solution. Okay, and why are there 4 different ways? Why did he solve it 4 different ways? Well, it turns out there are 4 different ways of solving uh, there are 4 different kinds of transformations, which I just briefly touched on earlier, and they're in the mathematics. And so we also have a group structure. The 4 transformations form a group structure. Okay, and that's a little bit beyond the scope of the talk that I'm giving here today. I'm just kind of giving an overview of it. Okay. Now, what happens in the lever paradox is it occurs because of the inconsistent use of time and space transformations. And the real problem boils down to our little bad boy here, length contraction. Length contraction is false. It's completely wrong. It's not correct. And it's basically one of the big boo-boos of Einstein's theory. And what happens is that when Ossio did the transformations correctly, okay, it turns out there's no length contraction in his calculations. Okay, so by getting rid of length contraction, he was able to solve the lever paradox. That's kind of the big takeaway. Now, he doesn't really know in his paper, and this is kind of interesting. He doesn't really know exactly why these 4 transformations work. And he doesn't explain what he's doing mathematically. So it seems kind of like it's hocus pocus. And I spent a lot of time trying to make sense out of what he was doing and why these 4 transformations work. And that's kind of how I hit upon the whole idea of the basis and coordinate transformations and using the standard mathematics textbooks to solve this problem of the mathematics of relativity being false. Okay, so now I want to talk a little bit about the twin paradox. The twin paradox, this is the most celebrated problem, and probably more people have tried to solve this paradox and explain it away. Generally, what they wind up doing is explaining it away rather than actually solving it. But we're going to discover here that we have a solution to it. We can solve that problem, and it's based on mathematical errors. Okay. The twin paradox violates the unique identity element theorem. That's basically the fundamental problem. So you're trying to solve this problem, this paradox, and the stay-at-home twin on Earth has a different age than the traveling twin in space, but the ages need to be reversed, okay, according to special relativity. And this solution that they come up with, Einstein tried to solve it in 1918. No, it's all just a lot of hocus pocus. Okay, so we're gonna present here how we can solve the twin paradox problem very simply, very easily. The solution is in the correct theory, there is no difference in age between the twins to be expected, since time is invariant with respect to the reference frames in this theory. So time is absolute. So since time is absolute, there's going to be no difference in the ages if we calculate time correctly. What happens in special relativity and the paradox is that they don't have the correct way to measure and calculate time. All right. Why this theory is the correct one. The mathematics is copied from mathematical textbooks on linear algebra. So we already know it's rigorously correct. It produces the correct physical interpretation because it contains no paradoxes or math mistakes. It is clean math with no need for metaphysical mythology. So what happens in relativity is that they make up all these excuses for why these paradoxes occur. There's all this magical shifting of explanations. It's just a bunch of confusion. It's just a mess. Okay. Now here's another point: is as long as we stay within the single rest frame, we get the same results as the relativistic solutions. So essentially, we don't dispute any of the experimental results. The experimental results are the same because we're using the same mathematics, the same Lorentz transformations. What's different is we get rid of the mistakes. Okay, the mistakes are gotten rid of, the paradoxes go away. All right, I'm going to talk a little bit now about Dingle, and we'll get down to one of the basic mistakes here. And Dingle wrote a book on special relativity. It appeared in around 1940, and he had sort of been a kind of critic of the theory, but every time he stuck his head up and offered some criticism in an attempt to put it on the right track, so to speak, he got beaten down by the experts. And it wasn't until the 1950s after he retired, and I think this is really important, and that is that the Dingle controversies don't start until after he had retired. So he was no longer, in a position where they could get him fired. He didn't have any university to embarrass by creating these controversies. So he created this controversy about the twins paradox. And the controversy basically revolves around this first equation at the top, which is T prime equals beta. That's the Lorentz contraction, Lorentz factor times T. And this is the Lorentz transform from the rest frame to the moving frame. Okay. And so that says that time is in the moving frame is dilated relative to time in the rest frame. But then you also have this other equation, okay, that's T equals beta T prime, which they call the inverse transformation, the inverse Lorentz transformation. It's not an inverse transformation. That's kind of a lie. And you notice that these equations are the same. All you did was exchange the T primed and the T. Okay, and the reason for that is the principle of relativity. Okay, because Einstein says that any frame is as good as any other frame, and so I can just exchange the designations, the symbol designations in symmetry and get the same equation back. Well, this does not work. So the principle of relativity produces a math mistake. Okay, these equations don't have a solution. These two equations do not have a solution other than the solution V equals 0, which means you have no motion. So when V equals 0, T prime, beta equals 1, V equals 0, beta equals 1. Okay, so you get T prime equals T and T equals T prime. Yeah, but no other solutions exist. Relativists refuse to accept that. They say, no, that's not valid because relativity of simultaneity. That's one of their excuses. well, time is relative, so therefore these equations, anyway, I don't want to go into their excuses. Okay, what's interesting about this is that Dingle's point was that these two equations say that a clock in the moving frame is working slower than the clock in the rest frame. And the second equation says that the clock in the rest frame is working slower than the clock in the moving frame. And it's impossible for this to happen, that the different clocks can both be working slower than the other clock. And this is the famous Dingle controversy, is what he said. And they tried to refute that. So McCrae produced a proof that Dingle was wrong. And in his proof, he discovered that V equals 0 was the only mutual solution for these two equations. That's where this V equals 0 comes from. That's where, when I saw this proof that McCrae did, where he thought he was refuting Dingle, what he did was he refuted special relativity. But he didn't realize that because he wasn't trying to refute special relativity, he was trying to refute Dingle. Okay, so there's no, so I've talked about that. The SR evasion is relativity of simultaneity, and the proof. So these two equations don't work. Okay, all right. All right, I've got this slide out of position here. Okay, all right. So here's the length contraction mistake. Now, for length contraction, they give us these two equations. And I think I've written, oh, yes, right. Again, we have a symmetrical pair of equations, except for the length in the moving frame. The L prime is contracted relative to the length in the rest frame. And then we have the symmetrical equation saying that the length in the rest frame is contracted relative to the length in the moving frame. So it doesn't make sense that the length would be shorter in the moving frame than in the rest frame, and that the length would be shorter in the rest frame rather than the moving frame. This doesn't make any sense. It's the same paradox that we had before. And these equations only have the solution V equals 0. And again, we're back to the same argument that applied for time, which is the only way these equations, you get a solution or a consistent solution of these equations is when there's no velocity. V equals 1. And of course, if the velocity is 0, that's a meaningless or trivial solution. All right, we're going to show how these things get fixed, hopefully, at some point. All right, now, Sachs and Harada. Harada is this Japanese guy, Mendel Sachs. Probably people have heard of Mendel Sachs, who was a physicist. And he kind of initiated a controversy in the late 60s, early 70s about the twin paradox. He tried to solve the twin paradox, and it didn't really go too well for him. They kind of rejected his solution. Anyway, about in the mid 90s, there was a proposal to solve some of the problems in special relativity. And one of them was they proposed that the units of measure are different in the rest and the moving frames, as opposed to the convention of using the same space-time units in all reference frames. Okay, that's the physical mistake right there. And it's not what's causing these paradoxes and these problems in special relativity is the assumption that the units of measure are the same in all the inertial frames. And he and Harada and Sachs are proposing that the units of measure are not the same in all of the inertial frames. So they say the units of measure change. Okay, so they reject Einstein's notion of relative time and space and propose this formula. A meter at rest equals 1 over beta meter in motion. Okay, so this is a length contraction. Okay, so what he's saying is that a meter measure rod at rest, when it's in motion, the scale is contracted by the factor 1 over beta. Okay, and then they say 1 second at rest equals 1 over beta seconds in motion. Okay, so they're saying that the second in the moving frame is less than a second in the rest frame. Now, you can see there's a problem here with this. Their solution was to introduce separate units of length and time for each reference frame. And they didn't talk about the 4 different transforms. So this kind of, and I pointed out there's a problem here in that these proposals seem to be wrong. In other words, a meter at rest is contracted in the moving frame. That seems right for length contraction, but it doesn't seem right for time dilation. So you could sort of say they didn't really have the correct solution. They just had a kind of thought this may help solve the problem, but they didn't really propose it in a way that was very clear, and it doesn't really lead to a solution. Okay. I'm going to try to explain now what the 4 transforms mean. And I'm sort of simplifying the mathematics here. So we'll just move on here. So the first equation, which is t prime equals beta t, is a basis transform. What basis means is it's changing the unit of measure. And I'm using basis transform because that's the mathematical terminology that's used in the textbooks. And that means that 1 second at rest is beta seconds in motion. So moving seconds are longer, they're dilated. So moving seconds are dilated. Okay, now we have another equation here, which is t equals beta t prime. Now, one of the things that you're going to find out here, this is kind of, the t's don't really mean the same thing. That's another complication that you have to dig into the mathematics for. But here we have a coordinate transform. So t equals beta t prime. That's the coordinate transform. That means the number of seconds counted at rest. So I have a clock in the rest frame and it counts seconds. And in the moving frame, I've got beta seconds counted. More seconds are counted in the rest frame. Okay, so I think maybe, okay, coordinate transformation means the number of seconds counted in the rest frame, okay, is greater than the number of seconds counted in the moving frame. Because the moving frame seconds are longer, fewer of them are counted on the clock. All right. Then we have the third transformation. This is the inverse basis transform, and it says that the t equals t prime divided by beta. It means that 1 second in motion, 1 second in the moving frame is 1 over beta second in motion. Okay. So rest seconds are shorter. Rest seconds are shorter. So in other words, in terms of moving frame seconds, rest seconds are shorter. Okay, then we have the fourth transformation here, which is another coordinate transform, means that the number of seconds counted in motion equals 1 over beta seconds counted at rest. Hence, fewer seconds are counted on the clock in the moving frame. Okay. So this is the 4 transforms. Now I think we're coming up here We should be ending here pretty soon, I think. All right, does anybody, I'm going to stop here. Does anybody have any comments or questions about the four transforms and how these things work together? So in other words, what this means is that the units of time are changing in an inverse manner. Okay, so going from the rest frame to the moving frame, the units of measure are longer. Going from the moving frame to the rest frame, the units are shorter. And then because of that, the number of seconds that are counted on a clock is the reverse of that. So fewer seconds are recorded in the moving frame than in the rest frame. And that's where these four transforms come from. Now, there's also four transforms that deal with length. Okay. And so what that means is that I measure in the moving frame, my measure of distance, my standard unit of measure of distance is longer in the moving frame and shorter in the rest frame. So when I go backwards, and so what that means is that fewer units of measure are counted in the moving frame, which looks like length contraction. That's where the mistake comes from. The length contraction mistake is that they're confusing basis transform with the coordinate transform. So when they talk about length contraction, what they mean is the number of units on the measuring rod that are measured are contracted, but the size of the units on the measuring stick are bigger. Okay.
Question. In the second and third and the pair and the first and fourth equations in your transform list appear to contradict each other.
There's no contradiction because it's provably correct mathematics. If there's a contradiction, it's a mistake when I wrote it down.
Well, consider the second and the third. It looks like you're multiplying times beta in one, and you're dividing by beta in the other.
Like I said, if you think it's wrong, I go to a math book and figure it out.
Is this a theory that you accept?
It's in the math books. Yes, I accept it.
I mean,
it's provably correct mathematics.
So you accept time dilation?
No, there's no time dilation. All it changes is the clock is measuring seconds differently. There's no time dilation. So in GPS, when they do the experiment and they say, oh, the clock is running slower, that's not time dilation. That's just a physical effect that happens to the clock. And you can fix that by adjusting the clock, which is what they do in GPS. They change the scale factor of the clock. The calibration of the clock is changed so that the seconds at rest equal this. It's kind of complicated. What they do is they make the second when it's on the Earth smaller so that when it's in orbit, it'll be the same as the second on the Earth because of the dilation effect. So they cancel out. So they make the clock run faster when it's on the Earth so that when it's in orbit and it runs slower, that it runs the same as the clock on the Earth as the clock in the orbit because of the adjustment factor cancels out the slowing of the clock. So it turns out to run. Does that make sense to you? It's kind of difficult to
yeah. It sounds similar. We only have like a couple seconds. Well, it sounds similar to time dilation, though. I mean,
time dilation says that time. All right, Jerry, did I answer your question or perhaps not?
Oh, yeah. Well, as far as GPS goes, I mean, of course, many relativists say that it accounts for time dilation and other relativistic effects. How do you know?
Well, that's because they lie.
Yeah.
I mean, let's be honest, they're liars. They use bad mathematics and bad physics and bad metaphysics. They're just liars in all three camps. And then because they don't really know what they're talking about, which is a problem because they think they understood Einstein, but Einstein is kind of hard to make sense out of what he's saying because, as I said before, Einstein thinks backwards. Yeah, anytime you read anything or try to figure out anything in Einstein's book, paper, his 1905 paper, or any of that, you have to realize he does everything backwards. A normal person wouldn't do things the way Einstein does things. He thinks backwards. Everything he does is backwards. Because he does things backwards and confuses things, it's kind of hard to make sense out of what he's saying. Okay. Then when you try to refute him, because he does things backwards and illogically, you can't really refute him because you can't really figure out what it was that he really said to begin with. Okay. And so you get all mixed up and your whole argument just kind of looks like it's, a confused, illogical mess. It's not your refutation of Einstein that's wrong. It's his backwards way of doing things that's wrong.
I can see how you're endeavoring to formulate a more rational system and maybe get rid of all these paradoxes of special relativity. But frankly, I view, say, Lorentz ether theory as a halfway house to special relativity. And I don't accept it, actually. I don't accept the Lorentz transformations. I think they're just, a trick, a quick fix. They're unnecessary. I think the...
Okay.
Yeah.
I don't really want to get into the philosophical issue here. The point is, this fixes the mistakes that exist in the current special relativity. And to do that and to fix his mistakes and his errors, you need these assumptions. You need to go and you need to use the Lorentz theory as the background. Now, whether or not you want to philosophically agree with that or not, I think that's an issue we can discuss.
Well, I don't know if it's just philosophical, Harry. I mean, in doing that, you've developed another theory, which at least I would say is erroneous as well. It's practically as bad as SRT. It's introducing something that's unnecessary.
Why?
Maybe that's philosophical. Okay. Maybe it's physical.
Well, philosophy is intertwined with science. I mean, philosophy, if it's correct philosophy and you're dealing with science, they should coalesce. I would say. I would say I agree with Ian. I don't really accept the Lorentz transformations either.
Well, the reason you don't accept Lorentz transformations is because you think they have something to do with time dilation and space contraction, which they don't.
I don't see why the units of measurement would transform, though.
The units, well, that's what the Lorentz transformations do. They change
Well,
the units.
the original Lorentz transformations were meant to account for the invariance of C, and you don't even accept that, though.
Now, what the Lorentz transformations do is they make the velocity of light C in the new transformed variables. That's really what Voigt was doing when he was doing his transformation, which I didn't really talk about Voigt, because I'm trying to make this simple and just explain what the mathematics is doing. Okay, now what happens is that when you substitute these changed variables, in other words, the change space and time coordinate measures into the equations, it turns out that the Galilean transform works. And so what happens is what you've done is you're really changing the variables so you can use the existing mathematics. So in other words, you can use Maxwell's equations. Okay. It makes Maxwell's equations invariant when the velocity of light is C. That's the whole point of this.
Is there any practical use? Is there any practical use for this?
Yes, GPS.
JPS.
GPS. You've heard of GPS, the global position.
Oh, GPS.
You've heard of that.
I thought that
It uses this theory.
I thought the Ron Hatch. So the whole Ron Hatch thing involves the Lorentz transformations.
Yeah, I don't know what Ron Hatch has to do with it. GPS uses this theory, but I haven't gotten to that point yet. You're busy trying to pick it apart and destroy it before you even understood what it's about. Okay. I lost my place here. Uh, all right. I think I've talked about all these things. Okay, you messed me up with asking all these questions. I can't find where I was. Okay, so we talked about Harada and Sachs. Physical meaning of the transforms. I think that's where we were at the last. And
Right.
I talked about, okay, there's, okay, the length contraction mistake. This is what I'm trying to get at. I was talking about this earlier. They confuse it turns out that length contraction mistakes the coordinate transformation for the basis transformation. Okay. They're not the same transformation. So what happened was that by mistaking the coordinate transformation, which is a contraction, because the coordinate contraction takes L prime, which is the number of measure units counted in the moving frame, is less than counted in the rest frame. Okay, because the measure units in the moving frame are bigger. Okay, but Einstein said, because Einstein assumes that the measure units are always the same, he assumed that this equation meant that length was shorter in the moving frame than in the rest frame, because he used the wrong equation, got the wrong equation. Okay. And now what's interesting is that it's not one of the symmetrical equations that I was talking about earlier. That would be L prime equals beta times L, which would be length dilation. That's the basis transform. Okay. Einstein confuses things by going backwards, defining length in the moving frame and showing that it's measured contracted in the rest frame. So which frame is it in contracted? That's kind of confusing. This is kind of confusing. The way he does things backwards, where he starts in the moving frame, goes to the rest frame, says that it's contracted in the rest frame. What? Because he does things backwards. All right. That's a lot of confusion there. This gets rid of the length contraction confusion. Okay, so what are the paradoxes? There's the twin paradox. We're going to get rid of the twin paradox, and we'll show how the lever paradox. We're going to get rid of the lever paradox because we don't have length contraction. Length contraction is inconsistent with time dilation. You have to have time dilation of the basis and length dilation of the basis. and you have to have contraction, dual contraction of the lengths. Okay. You can't have, if you do that, you get these paradoxes. Okay, we don't have those paradoxes in the correct theory. All right. All right. How do we get rid of the twin paradox? It turns out to be really easy. We have the equation T prime equals beta T. And these are the equations that we had, T equals beta T prime. They have no solution. Solution doesn't exist. And if we use these two equations, we'll get that the twin that's traveling in outer space will age less than the twin on the Earth. But we got the paradox that the twin on the Earth should be aging less than the twin on the spaceship. And then, so what they do to try to get rid of that paradox is say, well, the traveling twin is actually younger because he's the twin that's actually moving through space, which brings in the fact that space then becomes motion then becomes absolute, okay, which violates their assumption that motion isn't absolute or space isn't absolute. Okay, so we're going to use, if we use the four equations, the correct equations, we can correct the clock on the traveling twin's spaceship. So the traveling twin, we basically change the rate of time and the traveling twin's clock so that his clock runs faster when he's on the Earth. And so then when he gets out into outer space, his clock running slower, and it's adjusted by the correct factor, then his clock runs the same as the clock on the Earth. And therefore, he doesn't age differently from the twin on the Earth. So we have the equations that show how to do that in the correct theory. Relativity doesn't have the correct equations that show you how to do that. And we know that this is true and that we can do this because this is what GPS uses, the global positioning system. They change the rate of the clock that they put into orbit on the satellite so that when it runs slow in orbit, it is made to run fast on the ground so that when it runs slow in orbit, when it's in orbit, it runs at the same rate. And the equations that are used to do that are the basis change equations. Okay. So we said here, Einstein, okay, so we're going to summarize what's wrong with Einstein's math. He only has two equations, really, the two symmetrical equations. He doesn't have the four equations that's needed. Okay. And the reason is because he doesn't allow for the scale of the measurement scale to change. So he also has the wrong inverse Lorentz transformation. That gives you a lot of headaches. His claim that the speed of light is invariant produces incorrect interpretation of time and space. Okay. Yeah, that's the philosophical issue where Einstein says that time and space are changing. It's not the measurements that are changed, it's time and space. And then we have relativity of simultaneity, and that's kind of, that's used kind of as, well, you can't really criticize modern mathematics because relativity of a simultaneity allows the paradoxes. Okay. Rigorously correct mathematics requires group theory. Okay. In order, if you don't know what group theory is, well, that's the basic mathematical system. A group is a mathematical system that says that you have to have, every element has to have an inverse and you have an identity element. And the identity element basically defines how the inverses exist. The relativity has a group but it's called the rotation group. It doesn't really have the correct group to get the correct solutions. That's really kind of what the point is here. In other words, because the relativity principle violates the unique identity element theorem, you don't really have a group that you can use to construct a linear algebra. And when you try to do that without a unique identity element, you get paradoxes. And I talked about what those paradoxes are. Okay, so if we have a unique identity element, meaning one rest frame in the mathematics requires you have to have one rest frame. Can't have more than one, because if you do, you're going to get mistakes. Okay, and when we get to the linear algebra part, where we have the transformation of the basis and the coordinates, we have to have 4 of these transformations. And I tried to explain why there are 4 transformations. SR uses a rotation group, but that's not a linear algebra. So SR works, but it only works within one frame of reference. You can't transform between frames of reference correctly with SR. That's really the big problem. That's really what's wrong with the math. Okay, and that arises from the violation of the unique identity element theorem. Okay, so I'm going to summarize. The equations of SRs are not true inverses that you need in linear algebra. And instead of being a linear algebra, SR is actually only a rotation group. So really what happens is they try to use it as linear algebra when it's really only a rotation group. And a rotation group doesn't have the power that a linear algebra does. So that's really kind of where the problem was. It doesn't really have rigorously correct theorems in it, and we know that because if it did, they'd know that the solution to those 2 equations, the Dingle argument, it would be correct. Okay, there's no solutions to the SR equations because Dingle said that the moving clock has to run slower than the rest clock, and the rest clock has to run slower than the moving clock. That makes no sense at all. Okay, that's a logical contradiction. Well, the mathematics demonstrates that's incorrect. Okay, why they want to continue to hold on to that is amazing to me. Okay, that's probably one of the big paradoxes. There are other paradoxes. There's paradoxes of length. Okay, there's the pole and barn paradox, the astronaut and the hole paradox. I don't know if you're familiar with these paradoxes, but they're all basically due to the result that the mathematics is incorrect. Okay, there's no time dilation or contraction of space. We don't need those ideas. That's not what's happening. Those are metaphysical concepts. Okay, I'm going to finish up here talking about this Newton metaphysics is the correct metaphysics we should be using. And the reason is because Newton basically knew he needed his absolute space and time in order to solve mathematics equations. So I would say basically Newton understood the need for the unique identity element theorem in order for his mathematics to work. So he had to have absolute space and time. He knew that he needed that in order to get his math to work. And that's, I think, a point that people don't really get. Time and space need to be absolute and don't change due to motion in order to get correct mathematics to work. Okay, the correct theory indicates that measurement scales or units of measure are changed by the Lorentz transformations, not time or space. So time and space aren't changing, just measure units are changing. Okay, the theory is a theory of measurement and it's not metaphysics. So, okay, the problem with Einstein is that really basically it's a theory of metaphysics. It's not really physics. And somehow or another, he managed to get the right equations, which he borrowed from Voigt and Lorentz, and kind of packaged them together in a way that. And then Minkowski kind of helped him by inventing this strange mathematics that Minkowski invented that doesn't really work. Okay, so we have the illogical, philosophically messed up, and mathematically error-filled special relativity theory can be replaced by a mathematically rigorous, physically correct theory that does not involve paradoxes and metaphysical absurdities, while at the same time simplifies the physical principles and makes the mathematics easier to comprehend and use. This can be done while continuing to pass all the experimental tests. Now, I suspect you guys don't believe any of this. But this is at least a step in we're trying to move forward here rather than just saying special relativity is wrong, but we don't have a solution. Okay, here's a solution. It's based on rigorously correct mathematics. All right, that's the end of it. Okay, so since there's no comments, I guess everybody agrees with me that I'm right.
I think you rather doubt that, Harry.
Huh?
I think you rather doubt that. I think you're being a bit ironic there.
No, this solves. If you want to go with the Lorentz transform, okay. If you want to accept that the Lorentz transform is correct, and you want to go with Lorentz's solution to the problem, okay, that's the historical solution. Einstein sent the thing off the rails. Okay, that's the bottom line. What Einstein did was he made a bunch of mistakes, sent the whole thing, introduced new metaphysics, okay, that were wrong ideas, wrong, and did his math wrong, okay, and then Minkowski stepped in and tried to come up with this math theory, this Minkowski space stuff. Minkowski space, it produces this. The only correct solution is v equals 0. Okay, it's just so if you want to continue to use bad mathematics, Einstein's theory is the way to go. It's just bad mathematics. It's just okay, and basically this is probably the only way you can fix it, and actually substitute good mathematics for bad mathematics, because it's based on what the math books say. It's based on what's in the math books.
Well,
As I say, it's a more rational system, but in a way it could be conceived of as trying to save, not special relativity, which is what the mainstream do, but to save the concept of Lorentz transformations and Lorentz's work, whatever about Voigt's earlier work. And I don't think that's necessary. I think we should be more fundamentally concerned with that, and we should actually ditch those concepts as being erroneous. But
okay, so you want to ditch all of the experimental verifications and try to tell physicists that their theory of particle physics and relativistic particle dynamics and all that is ditch all that because it's all based on special relativity. The problem is that all works out and seems to be correct, okay, and they don't want to ditch it. If you say special relativity is wrong, they look and they say, well, wait a minute, that means we'd have to redo all of particle physics and all these experiments that verify particle physics is correct, okay, it's all based on Lorentz transformation. Well, it's based on their Minkowski space interpretation of the Lorentz transformations. Okay, you're asking them to ditch all that, and they haven't ditched it.
I don't think that particle physics is based upon Minkowski space or the Lorentz transformation. If you read the history of particle physics, these things are barely even mentioned. Or in fact, they're probably not mentioned at all. Particle
Okay.
physics has an entirely different body of experimental evidence upon which it is based. You can go back to the discovery of the so-called discovery of the electron, for example. This has nothing to do with this math, with these transformations, Minkowski space, none of it. And so you have to state that you have to throw out decades of very fundamental particle physics research because of some math question is without foundation, in my opinion.
Well, I'm going to just say you're wrong. Okay. Anybody other comments?
Lorenz himself didn't believe in that the units of measurement transform. He thought that objects contract in length and grow in size.
Yeah, that's kind of where Einstein got his mistake from.
Well, why were the Lorentz transformations necessary, though? What problems do they
The
solve?
Lorentz transformations basically make Maxwell's equations invariant. So if you really want to, get down to the bottom line, as you could say, Maxwell's equations are wrong. But what happens is that you make the Lorentz transformation makes C the same in the moving frame as it is in the rest frame. But
I thought you disagreed.
hold on. That's a mathematical trick, if you will. You could say that's a mathematical trick. Making the velocity of light C when it's not C is a math trick. Okay? But when you substitute the transformed variables into the equations, into the standard equations that they use, you get that the equations work correctly. Okay, that's why the physics community uses Einstein's theory. Unfortunately, his metaphysics is all screwed up. His assumptions about principle of relativity, speed of light being the same, that's all bogus malarkey. So what physics has done is that it has brought in all this metaphysical nonsense, all this baggage, okay, and put it into physics books telling us that time is relative to motion and time dilates and space contracts and all this other stuff. That's all BS that Einstein baggage that he brought with it. Now, if we use this approach, we get rid of all the baggage and the physicists can still use their equations, but we don't have all this time dilation, twin paradox, all these paradoxes, all these metaphysical illusions anymore because we don't talk about time and space changing.
Well, if the units of measurement transform and objects don't, and okay, if the units of measurement get smaller when the object travels away relative to the preferred frame or wherever, if they get smaller, why wouldn't the objects appear to grow? Like, why wouldn't their apparent size be altered if the units of measurement transform?
All right. You're completely confused as to what is meant.
Okay.
The object doesn't change. Okay.
But if the units of measurement transform, the objects wouldn't fit in there the same
All right.
way.
You see here, I've got a ruler.
Yeah.
Okay. It's got different scales on it. Okay. That's what the units of measurement are. They're just arbitrary things that are put on this ruler. Okay. There's this thing called inches. There's 12 inches on this
Really?
ruler. Right. It's a 12-inch ruler. That's 1 foot. Okay.
Yeah.
So 1 foot is 12 inches. Right?
Okay.
Okay, so I can use feet. I can say my unit of measure is 1, or I can say my unit of measure is 12.
Why don't objects outgrow their
But that didn't change
smaller units of measurement?
That didn't change the length of the ruler, whether I said that it was had a length of 12 or it had a length of 1. It's still the same.
What is the point of the theory, though? What does it solve?
It solves the mistakes that Einstein made in his confusion of how to use mathematical transformation equations.
See, another angle, I don't know if I'm simplifying it too much, is that it may be strategic. I may have taken you up wrongly, but I've been speaking to Professor Hallam Bhuta on this as well, about maybe bringing along the mainstream in a way that I would actually support. We tend to be a bit cock a bull going in and shouting and so on, bringing them around. But I believe you're making too many concessions to the existing ways of thinking. And I mean, for my part, I would consider that atomic clocks, the behavior of atomic clocks, is a physical phenomenon that can be investigated. It should be investigated further, actually, because we're not quite sure. But
Oh, you don't believe that Lorentz transforms describe the
no, I don't. They just coincidentally have a similar mathematical.
All right, well, that's an argument that you can make. I'm not arguing about what the ultimate physics is. I'm merely pointing out how to fix Einstein's screwed up mathematics.
But why are you trying to do that? Is it to bring along the mainstream?
Why am I trying to do that? Because they don't want to change. They've invested themselves in this screwed up metaphysics and mathematics and going around telling people about motion causes time to change and space contracts and you have time dilation and all this stuff, mass
so it is sort of a strategic endeavor to try to confuse them, but lead them along to give them the impression that you're not actually completely destroying their complete foundation of physics. And
it's destroying their stupid metaphysics. Their idea that, Newton was wrong and Einstein was right. And how is it that Einstein's right when you can't make sense out of his mathematics? I mean, his 1905 was Alistair Beale showed that his mathematics in his 1905 paper is complete nonsense. I mean, nobody really can understand what he did in his 1905 paper. It's just full of math errors. Okay.
Beale is giving another talk, by the way, in a few weeks' time. Just thought I'd tell you that.
The point is, there's so many mistakes in Einstein's theory, you really can't trust it. But it's really basically got these philosophical blunders at the beginning. I mean, he comes along and says, Newton's wrong. How is Newton wrong? Because I say Newton is wrong. And then he invents this mathematical theory that's full of mistakes to explain the correct theory. And these people believed it. I mean, it's just kind of because the Lorentz transformation has some validity in physical experiments. In other words, they show that the Lorentz transformation works in physical experiments. And so
what besides GPS?
Huh?
What besides GPS? What experiments?
Well, it's used, despite what Jim said, it's used quite extensively in particle physics calculations and accelerators. And one of their favorite quotes is, every day, thousands and thousands of experiments, every day in every way, the theory of relativity is verified by particle accelerator experiments because that's the theory they use.
They say the theory of relativity is being verified every day in the particle accelerators. And you, I think, Harry, if I may say so, are saying that this modified interpretation of Lorentzian ether theory is being verified every day in these particle accelerators.
It's not.
Those conceptions.
It's not Lorentzian ether theory. It's just the Lorentz hypothesis that there's a rest frame.
See, I agree with your slide on the Newtonian concepts. I think your first two bullets about absolute space and all that, I agree with that totally. But I think your next two bullets I disagree with because you're trying to reinterpret a Lorentz transformation to be consistent with that, which
I'm
is
not, I'm not
valuable
trying
thing
to
do.
reinterpret it. I'm just pointing out that the mathematics requires a reinterpretation.
But why not ditch it altogether? I mean, I claim I've shown that Lorentz's transformations are just a quick fix. They're, a
I'm
misconception.
not saying they're anything other than that. My point is that the Lorentz transformations don't tell you that time and space are changing. They tell you that the measurements are different. How you need to apply the measurements is different.
Well,
Time
that's
and
one way
space
of
don't
interpreting it.
change. Time and space don't change. They're always the same. But the way you measure them, the way you quote the measurements in the moving frame and the rest frame, you need to have different units when you use the Lorentz transformation. The Lorentz transformation changes the units, doesn't change space and time.
Harry, if the units get exponentially smaller, the faster that an object goes away from the preferred frame or another object or observer, why don't the units of measurement grow in length when they go the opposite direction?
I have no idea what you're talking about.
Okay, you know the way the units of measurement shorten, correct?
The units of measurement shortening is just a mathematical device.
Yeah. Why don't they
You
extend in
understand
length
that?
in the opposite direction? Why don't they extend in length in the opposite direction though?
Well, they do when you go backwards from the moving frame to the rest frame.
Well, I haven't. I've looked it up, and that isn't the way the theory goes.
Well, that's why I'm
Rest
saying
frame.
the theory's wrong.
Well, the Lorentz transformations. I mean, you're the first person I've ever heard say that the units of measurement grow when they go in the opposite direction.
Well, it's the point. This is the issue that's problematic. That what happens is when you put the Lorentz transformed units, in other words, you change the variables. Okay, when you put those changed variables into the standard equations that they use, okay, for conservation of energy and conservation of momentum and time and space, when they put those transformed units in, they can use the Newtonian equations and it works out and they get the answers that agree with experiments. That's why they use the theory of relativity. The problem is that from what Einstein is saying is that it's not the units of measure that are changing, it's time and space are changing.
Yeah.
Well,
So
we all reject that, I think. We all reject that.
right. And so
The question of how you put the experiments into the straitjacket of conforming to Newtonian principles, which I think in general we agree with.
well, what Einstein says is that the laws of physics, his principle of relativity really is that the laws of physics are the same, okay, everywhere. That's kind of like a, article of faith, sure, all physicists are going to believe that. So
Well,
what
how aren't the laws of physics the same everywhere?
that's a postulate that's a foundation stone of physics.
Yeah. Why is it mistaken though?
I didn't say that it was mistaken.
Oh, okay. I'm sorry.
What the Lorentz transform does is allows them to use those laws. Okay. Okay, Jerry, let me, I didn't put this example. I'm going to try to answer your question. I didn't give this example, but it turns out that one of the famous things that they talk about is about the Galilean transformation, that the Galilean transformation doesn't work at high velocities. Well, one of the things I discovered was that if you substitute the transformed variables, in other words, you transform the variables and you substitute the transformed variables into the Galilean equation, the Galilean equation works. So what all relativity is doing is it's using the equations, the standard equations of physics, but instead of putting the variables at rest or the rest variables, it changes the variables when you're moving at a high velocity. So time and space variables that go into the equations are not the same time and space variables that are used when you do the calculations at rest. I'm not sure if that helps you to understand. That's what is meant by changing the units of measure. Okay, you're changing the mathematical variables that go into the equations, and when you do that, the equations remain valid at high velocities rather than being invalid at high velocities. Did that help you any?
Well, I've read over and over and extensively interacted with ChatGPT about how the Lorentz transformations were meant to account for the invariance of C. And if they don't, why were they developed?
Okay, I thought I explained this in the beginning. Einstein does things backwards. Okay, he assumed that the velocity of light was c physically the same in different frames of reference in motion. That's not true.
Yeah.
But when he did that, in order to make that make sense, okay, because it's ridiculous for you to even consider, how can the speed of light be the same if I'm moving or if I'm not moving? How can I measure the speed of light the same? Einstein says, well, it's true, but what happens is time and space are changing.
Yeah. Well, I thought you had said that C is invariant with
You have to, now
frame.
he's doing it backwards. He's
Well, I
talking
mean,
the Lorentz transformations backwards.
you've said though that C is invariant within the ECI frame though. You've said that before.
Yeah, that's the rest frame.
Yeah. Well, the ECI
Whereas
frame,
Lorentz said the speed of light is invariant in all inertial frames, but he then added that this is something that cannot be accepted without a considerable degree of hesitation.
Well, it makes no sense.
Yeah,
So,
he said it, and then he said it makes no sense as well.
but if you change, what Lorentz did was Lorentz changed the variables in which and the variables which you're using in your calculations in the moving frame are not the same. They don't mean the same thing. The units of measure are not the same in the moving frame as in the rest frame. If you put in those transformed variables in the moving frame, you get the same velocity of light c as you do in the rest frame. That's what the Lorentz transformation does. And when you do that, you can use the Maxwell's equations and you can use this equations of physics that appear in Newtonian physics, and you can use those equations, but the variables that you're using are not the same in the rest frame that you're using in the moving frame. So do you understand what that's about?
Yes, and as you said earlier, Lorentz basically developed these transformations to transform Maxwell's equations in different frames of reference. So you have an invariance of form. But then when he found these things, or I suppose they really are copied from Voigt with a very slight change, but when he found these things, they become like godlike, that so they must be true in all circumstances. And then when you find that there are certain strange things, like that the speed of light does not depend on the motion of the observer relative to it, you say that cannot be accepted without a great skepticism. But on the other hand, we know that the Lorentz transformations work fundamentally in physics, so we'll have to accept them provisionally. But I would say no, they're an erroneous quick fix to something.
Well,
As I
calling
said,
them an erroneous quick fix is basically what they are, but they're they're used because they want to keep the laws of physics the same. The laws of physics, we don't want to invent new laws of physics when we're moving at the speed of light. So what we do is we have this Lorentz transformation. And when we use this Lorentz transformation, it allows us to use the same laws of physics when we were going slow as when we're going fast.
so then is your contention to adopt them and then to reinterpret them so you get back to the rational absolutivity of Newtonian physics, to do that rather than ditch them altogether? Is your preference in doing the former merely to bring along the mainstream?
I'm merely pointing out what the correct mathematics is.
Yeah,
Whether you want to accept the correct mathematics for philosophical reasons, which appears to be your difficulty, is not my issue here in this presentation. My point is, let's use the correct mathematics. Once we use the correct mathematics, then we can decide whether it's good physics or not. At the present time, they're not even using correct mathematics.
Yeah, I mean, hypothetically, if I were forced to accept the form of these transformations, I would accept the correct mathematics and go along totally with you. That's true. But I'm not ab initio forced to accept the form of them. I'm going to ditch them altogether, just the way I ditched
Well,
SR.
that you can obviously you can choose to do that. I'm merely pointing out that this is how we get to the correct mathematics. Okay, this is what the correct mathematics shows. Einstein uses incorrect mathematics, and so we don't really know what that shows. It just
Well, there's
shows
a
a lot
lot
of
of correct
mistakes.
mathematics. There's a lot of correct mathematics which are not used in physics at all. Mathematicians have a life of their own, and there's theories all over the place that if you want to go into what mathematicians are doing, and so just because mathematics is correct is not necessarily relevant to physics. And if you use another issue I'd like to raise, or question, if you will, is if you're going to use time as a sort of position coordinate in a four-dimensional position coordinate, adding time, then you have no laws of physics. You've used time as a position coordinate. Laws of physics have to do with change in the system state over time, but you've used time as a position coordinate. So there are no laws of physics to even worry about if you're using the Lorentz transformation as any kind of a basis.
You're confusing the Lorentz transformation with the Einstein interpretation of it. What you just said is the relativistic interpretation of time. That's not what I'm talking about. What I'm talking about is when you use time as absolute, and we have the correct mathematics to describe it. So you just pointed out a good reason why we need to ditch relativity.
Yeah, it sounds like you're actually providing a strong argument to favor the whole approach of binary mechanics, and I appreciate that, and I thank you for that.
Well, the point is that time and space are absolute, okay, and it's Newtonian, okay. So we have Newtonian. A large part of the issue has to do with there's this dissatisfaction of Newtonian-based physics towards the end of the 19th century. And you have, and I can't remember all the people who were involved. Mach, I think, was one. And there was a lot of criticism of Newtonian physics towards the end of the 19th century, as I was trying to say. And Einstein sort of stepped into this period when people were looking for like, oh, something must be wrong with Newtonian physics. We don't really like it. You know, they could look at a lot of philosophical reasons why it was wrong. And Einstein came in and said, well, let's get rid of Newtonian's absolute space and absolute time and create this new theory. And I think that basically they were receptive to that because there was, a lot of how should I put it, unsettled feelings about Newtonian physics and the assumptions behind it. Absolute space and time being one of the ones that was criticized. So Einstein says, let's have relative space and time. And they go, yay. And so he constructed this theory, okay, and with bad mathematics, I mean, really bad mathematics, and came up with time dilates and space contracts. Well, space contraction is a complete mistake, and I may have made a mistake in combining that with the other mistakes, but that mistake I think came out of the Lorentz contraction hypothesis. So, in other words, if Einstein said, "Well, space contracts," that agrees with what Lorentz and that Lorentz-Fitzgerald hypothesis. So that agrees with that. So that sounds like a good thing to put in there. So I'll put that in there. But what happens is, and I tried to explain this, maybe I didn't explain it very well, you get this lever paradox and these paradoxes in what are called relativistic statics. And they're caused by the fact that in the equations, they assume length contraction. And length contraction doesn't work. It gives you the wrong answer. And so what happens is they get these paradoxes. A good example is the lever paradox, which is what Hassio by I was talking about. And he was able to resolve it by essentially doing the calculations correctly using his 4 transformations. And his 4 transformations that he uses are essentially the 4 transformations that I talk about: the basis transformations and the coordinate transformations. There's a forward transformation and a reverse transformation for each of the basis and each of the coordinates. And that explains why Hassio by I solved the problem with his 4 different methods. He cites 4 different ways to get rid of the paradox, but he didn't really understand where the equations came from that solved it.
Doesn't it all go back to Michelson-Morley, though?
Well, Einstein came up with a screwed up theory before that, I think.
No, his was supposedly to solve the null results.
After he published his 1905 paper, then he started publishing papers where he used the Michelson-Morley experiment as justification to say that his principle of relativity.
That's not the way I read his 1905 paper, but
well, does he cite the Michelson-Morley experiment in his 1905?
He doesn't cite anything in it.
no, he in effect by saying
Well,
that
Jim,
two-way
I
speed
think
of
you're
light
wrong.
is the same.
Well, I think Michelson-Morley
I'm going to come out and
experiment.
flatly say I think you're wrong.
Sorry,
I think
did you hear what I said? He cites it by saying that the two-way speed of light is the same.
Well, you're just saying stuff to justify.
No, that's what that's his main.
That could apply to that for sure.
Well, Jim, I'm afraid I have to tell you you're wrong.
Well,
But
I think
read some more. Read some more, Jim. I think everything that you talk about every time you come on, you go about Michelson-Morley. Oh, that's the solution to everything. No, it's bigger
right,
than
well,
that. You don't know
I'll
what
leave
you're
then.
talking about.
I'm sorry if I upset you.
Oh, don't leave.
But getting back to the Einstein business, I mean, whether you like or dislike his arguments, or whether you think they're backwards or rational or not, it can be cogently argued that he actually, contrary to current belief, he actually didn't introduce anything fundamentally new. I think it was T.K. Whittaker who said that in the early years of the 20th century, Albert Einstein wrote a paper just rehashing the views of Lorentz and Poincaré and Larmor, and a lot of fuss was made about it. So perhaps that's really what he did. He just rehashed the views which were already around, and he added his own, ideas or idiosyncrasies, which you may take exception to. But the original conception of things like length contraction, of course, were Fitzgerald's and Lorentz's, as we well know, and he just incorporated that, as you yourself said earlier, Harry.
Well,
wasn't the Michelson-Morley wasn't the Michelson-Morley experiment designed to um, back up Einstein's theory, to test for an ether, and if there wasn't an ether, then Einstein was right? That was
Einstein was
the
20 years after the Michelson-Morley experiment. In fact, it was 30 years after the first experiment in 1881. So no, that's I think what Jim might have been saying, that or was it Jerry, that Einstein's ideas were partly in response to the Michelson-Morley experiment, and he didn't acknowledge that. The main experiment was 1887.
All right, but now we're off on the tangent. This is what happens when you talk about Einstein and people bring in these red herring side issues rather than to the what you're saying. Einstein, I think, introduced these ideas that were basically had been people had been talking about. He didn't invent the Lorentz transformation. Voigt had discovered that earlier. Lorentz had also worked on that. What Einstein did, I think, was he provided a different philosophical background to justify it. Does that make sense to you? In other words, he's got these postulates, and then it made it look like that if we adopt this non-Newtonian physical viewpoint, this non-Newtonian metaphysics, okay, then we can explain these things, and you put it into a nice looking package. But unfortunately, his math was done improperly, and they've spent over 100 years now trying to fix his math.
Well, Poincaré's 1904 paper, which was essentially the same, it led to the same principles. And Poincaré was one of the greatest mathematicians of his age. Would you say, Harry, that his mathematics was correct or wrong?
I don't really know that much about Poincaré. I can't comment on that. My point I'm making is that the interpretation that they've adopted is really based on a lot of math mistakes that originate from Einstein. And a lot of that has to do with the way he does things backwards. Anyway, it's very difficult to understand what he's doing because he doesn't do things in a straightforward manner.
What's an example? I don't know if I understand how he did things backwards. I
Well, he
mean,
does the Lorentz transformation backwards. He assumes that the speed of light is the same, and from that deduces that time and space change, when he really should have started from the point of view of what transformations of the variables for time and space do I need in order to make the velocity of light appear to be c and the moving frame and the rest frame. That's backwards. Do you understand that? Do I need to repeat it?
well, I don't see how that's necessarily construed as backwards. It's a different approach for sure.
Well, to me, it's backwards because he started with the wrong assumption that the speed of light is the same. From that, deduced that time and space are different.
Well, you mentioned that C is invariant within the ECI frame, though.
Yeah, C is in the rest frame, yes.
Well, the ECI frame extends everywhere. So that would mean that C is invariant everywhere.
Well, that's, you know, there's a lot of argument about that. We're just talking about the mathematics. That's the problem when you try to transfer. What you're trying to do is you're trying to transfer mathematical assumptions into physical assumptions.
Well, the math should describe the physical reality if it's truthful.
Yeah, but you have to have truthful
Yeah.
math first. That's the
But
problem.
the thing that people keep forgetting is math can represent non-realities, and
As well.
people have built theories upon their math that are just absolutely crazy, and we recognize that they're crazy for for using that math, but the math shows it correct, so they think it's correct. So, I mean, like I say, math is just a tool. Everybody puts math on a pedestal where it just needs to be put in a toolbox. Go ahead. Sorry.
Well, that's largely, my thesis is that the toolbox or the mathematical tools that you're using have to be correct. And if you don't use the correct ones, you get the wrong answer. That's what's happening here.
Yeah. And like I say, math can be used to prop up a false theory, a false reality, like black holes.
Yeah, but I do frequently think that Einstein's idiosyncrasies in the way he does things, whether it's backwards or extrapolating or whatever, has been very conducive to the acceptance of his theories. I mean, it's frequently talked about political expediency after the First World War and the 1919 experiments and so on. But I think, I mean, Lorentz's ether theory, which to me is essentially the same. It's a very big stepping stone towards SRT. Was never accepted popularly by ordinary people or by the scientific community in a popular sense. But hey, presto, Einstein comes in 1905, and it's accepted, and then in 1919 everything is validated and so on. So his way of thinking was a way that would persuade people. It's a very newsy. It's like the sort of thing you'd have on the internet now. Very quick sort of things put on YouTube where people don't want to think too much about things, but it springs to their mind. They could easily have read Lorentz's huge tome on the whole subject of electromagnetic radiation and his transformations and his whole theory of the universe and the electron, varying in absolute size according to its motion. In other words, a Lorentzian contraction because of the forces on the electron, and he works that out in great detail. But nobody has the wit or the bother to go into that. Just as they don't have the wit or bother to go into McCullough or O'Reilly or anything like that. But come Einstein, it's almost like a populist type thing, which impinges upon the popular mind very quickly, I think.
I think scientists like to wow people with the mysticism that they've created.
Or you could say scientists like to baffle people with bullshit.
Yeah, that's what I just said.
Sorry for being so curse.
Yeah, well, the populist scientists certainly do that. The people who are on the media and they get great following from the masses at large, if I may say so. And if one dares to criticize these popular scientists, one is put down very, very rapidly.
All right. So to summarize, Ian, I know you think I'm trying. I have no. I have no belief whether the Lorentz transformation is ultimately metaphysically correct. I do view it as a mathematical thing. It's a math. You could view it as a mathematical trick, so to speak. When you use the Lorentz transformation and you stick the transform variables into the equations, you get the right answer. Okay. And so in that context, it's kind of a mathematical trick. And the issue in my mind, and I think what the problematical issue is when scientists start talking about the nature of time. Like for instance, Don Lincoln recently put out a video a couple of days ago where he talks about time, and of course he talks about Newtonian time, and says, but of course we know that Newtonian time is wrong, and Einstein showed that time changes due to motion. Okay, and it's all just kind of metaphysical mysticism. How does time change? I mean, it didn't help me to understand what time is to have him tell me that time can change based on motion. That left me completely confused. Kind of my point that I'm making here is let's stick with the Lorentz transformation as a mathematical gimmick or a mathematical trick, if you will, and not have to bring along with its use a lot of metaphysical nonsense about time dilating and space contracting and curved space and all this other stuff. We don't, I mean, that's not physics in my mind. And to have physics talk about it and claim that it's so just doesn't make any sense to me.
Well, I'm certainly traditionally inclined to accept that if it will further the general thinking along these lines and get both physicists and the general community thinking about it. But ultimately, if I am asked, metaphysically about all these questions, I'll probably differ. I beg to differ.
Well, you're going to beg to differ with my postulate that time is absolute, time and space are absolute, and they don't change.
No, I accept those. Absolutely. Accept those, absolutely. It's just the metaphysical foundation behind that. I accept the Newtonian Galilean universe. And I introduce, it's a bit late now to start talking about it, but I introduce certain analyses within the electromagnetic sphere, to wit, a sort of a hydrodynamic model, Navier-Stokes type equations. And so what comes out there is an invariant system based on Galilean transformations, absolute time and absolute space, complete unnecessary Lorentzian transformation. And this, which I think is misleading us a lot, when we see this, GPS clock retardation, which seems to have the same form as the gamma factor in the Lorentz transformation, we can all be very excited. But that's a physical effect. And similarly for the muon decay rate, these are physical effects. They might have the same form. That's actually a common factor, this sort of 1 minus v squared over c squared. It comes into a lot of force equations. I think Kelly said if you kick a football against a wall or something and it becomes deformed, and then by elasticity you work out how it recovers, you get the same factor coming in. So it's perhaps not a pure coincidence. And that's how I would deal with it in a very, very deep form. But having said that, I'm provisionally happy to accept this as a way of maybe bringing people along to marrying
So you want to
experimental results with theory.
You want to hold on to the Hertzian solution, I guess it is.
I do, as you know, I do. Yeah, that's my
all right. Well, I'm just pointing out, I'm pointing out where the mistakes come from, why these paradoxes arise, the equations. Dingle was correct when he pointed out that the special theory of relativity requires that each of the two different clocks has to run slow with respect to the other. And he said, this doesn't make any sense. Okay. And of course, they argued about this during the 60s, and they won eventually. They pointed to the muon experiment, as proof that the special theory of relativity is correct, which is, in my mind, just a red herring. Those equations that they have don't work, but you can explain the muon experiment in terms of the mathematical system that I propose, because you don't have that those two equations that don't have a solution. Those two equations for time dilation have no solution. So they just avoid recognizing that fact. So a lot of these issues that you're dealing with when you talk about relativity are just based on math mistakes. Yeah.
And Dingle and Essen, raised these points very cogently, and they got a very poor response because they were hitting a raw nerve that there might be something fundamentally wrong. But yes, I agree with both of those statements.
All I'm doing is I'm trying to say, okay, Dissonance, I've talked about this before. This is really a long time. What I've noticed is dissidents don't want to hear about it. And, you talk about it with dissidents and you explain to them this is the correct solution, these are the correct equations and the correct way to use them. They don't want to hear it. Okay, so I'm just putting it on the record now. It's out there. It's at the General Science Journal. There are papers there. I've pointed out people need to read these papers. I pointed out these papers to Stephen Gift, okay, who I would have thought was somebody who would understand it. He said, "Oh, they're all wrong. They're incorrect. My Solari theory is the correct theory." He doesn't want to. He doesn't want to see what the correct mathematics is.
That's
And have you had any discussions with Hallam Boutayeb on this, Harry?
No, I haven't.
that's the problem with most dissidents is they have their own theory and they stick to it like, honey to.
Well, I have my theory. My theory is Einstein's theory is wrong, and I can tell. And I just told you why. Uh, it's just full of mistakes. Okay, we can't really move forward until we can figure out what the mistakes are. I'm not really sure that the mainstream is going to want to change what their textbooks say based on that. But I'm just, there is a correct mathematics out there. That's all I'm saying, and we should be using it, or the physics community should be using it.
Agreed.
All right, we're coming up to the end here. So that's the end of it. Okay, if you want more information, you go to the General Science Journal that discusses this. There's no real complete paper that discusses everything that I've talked about here today. This is really the most up-to-date summary of it. Probably not the best presentation. I tried to make it simple, but unfortunately it came out more complicated than I thought it would be, because it's difficult to explain. The mathematical theory of basis and coordinate transformations is not really that easy to understand. It involves a concept of duality, and they don't really explain what duality is, and they don't really explain very clearly what a dual transformation is, and dual space, mathematical dual spaces. And I've tried to kind of make it simple and not really get into the arcane details that are and this is not something you're going to find in your first year college algebra book. This is something that is more in advanced mathematics and requires, pretty much some effort to understand it. Well, you haven't said anything, Vladimir.
I want to ask a couple of questions but I'm patient today right now to hear some different ways to think about it. Let me ask you the question. Do we have a definition of time? What does it mean, time? We're talking about delay, this one, that one. Time is only parameter t in these equations. But I want to know physical meaning of time.
It's a definition that's agreed upon by treaties between nations.
Okay, thank you so much. It helps me as a physicist to understand what does it mean, time.
Well, when time was conceived of, it was when the sun came down and the sun went up. That was time. They measured time by those things.
Wrong.
Hang on. And then when we progressed into science, we started making clocks that are precision timepieces that kept time very well. We get into the atomic age. Time is now defined by the vibration of a cesium atom.
First of all, solar time, it doesn't work for cosmology because sun exists for 4.6 billion
We're
light
we're
years,
past solar
and
time. We're past solar time. We're into the atomic age where time is derived by the vibration of a cesium atom. That's how we
Okay.
keep time now.
Okay. So the bottom line is it's a definition that people agree
definition,
with.
you told me about the measurement tool, atoms, whatever, but I mean the notion of time.
The
Can you
passage of
explain it?
the passage of 1 second to the next. That's time.
In the notion time, there is no 1 second. There is a notion only. Please give me in words, what do you mean by time?
Well, I
Time
think Newton expressed this. I've forgotten the exact words, but
time
he
is
said
the
time which
expression.
progresses continuously, linearly, and is an absolute value. And you could look at an analogy between coordinate elements. The three basic dimensions. So that if you're looking at the separation between two points, you get a distance. It could be x, y, z. And if you're looking at the separation between two events, you get a separation which we can call t.
Progression of events. If you want to call it, talk about it simply, it's just the progression of events.
I would actually say that time is inevitable, whether there's physical phenomena around or not. I would say that time is the temporal order of existence.
Time would progress without us, yes.
Yeah.
Okay. Let me interrupt. Vladimir, are you asking for a physical definition of time or a philosophical definition of time?
Philosophical, let me tell, because if we have absolute time, absolute space, I want to know what does it mean. And what is important? Let me tell you the comment because I'm ready. I'm worried that I will not tell everything. I do like your lecture. And why? Because it does matter what is the mathematics. But if you put in physics some theory, it must be consistent. It must be solid. You're absolutely right. That's why I understood this perfectly. You took some mathematics, please go with a rigorous mathematics, solid mathematics, not with some bullshit around. And reverse means you took this constant, but where it came from his head, I mean, Einstein head.
All right.
Today, Harry, he showed us if you will do the right mathematics, you will get C, but it's a direct way to go. He was absolutely right. Let me ask you the question about the
You
general
got 1 minute.
relativity. Okay, the general relativity. It's usually telling that it's based on special relativity. All these mistakes with special relativity, how it will influence on the general relativity definitions, equations, and all this stuff.
That's a good question, but they use absolute time in cosmology.
Agree with absolute time, but time in me, it's not a fourth dimension. It's a factor of our world. It's a factor. They don't have in general relativity four-dimensional space-time. Forget it. It's a for manual. It's absolutely wrong definition even. That's why always I try to talk about the definitions. First of all, give me the definitions and rigorous mathematics, then I will believe to you.
All right. Okay, I want to thank everybody for coming